It's been my honor to be invited here. See so many young people. It's been a while. It's been a while to communicate with younger generation. Well, you're like 5 generations below me. So, anyways, I like to keep this talk a bit more inspirational, kind of a storytelling, than getting to the technical nitty-gritties of this machine learning, neural networks, and whatnot. That's boring. That kind of information you can easily get from Coursera, online courses, YouTube. I learned everything from YouTube after school. But back in the day, we didn't have the luxury of YouTube or internet or any of this information that's widely available to anyone that has internet connection. We didn't have the luxury. But anyways, I want to focus today's talk on drives. Growing up, we had to take classes, right? A bunch of classes, elementary school that we learn algebra, we learn arithmetics, not even math. Right? We learn things. And then throughout my learning experience and my learning, I wouldn't say the career by years, our teachers very rarely told us why we're learning all these things. So I want to focus on why. I want to give you an example of my math teacher in college. He taught engineering mathematics. And here's his teaching style. He's got a little note, and he will come to the office, the classroom, and he will go this. And he will just keep mumbling, like repeating what he wrote with no explanation. And then 15 minutes later, he's done with his blackboard. He turns around. Questions? Guess not. I didn't explain anything. How could there be any questions? So he starts to erase everything and then works on his second board. So it goes on and on. I was sitting in the back doing my little doodling because I wasn't paying attention to him. He gave me very, very little incentive in learning whatever he was teaching. At the time, he was teaching Fourier transform. I don't know if you guys heard about Fourier transform. Maybe calculus, BC, AP, not important, right? So he was talking about some really, really high-level mathematics crap on the whiteboard without explaining anything. I was thinking, if you want to go about this way, then why didn't you just give me a handout, right? Give me a handout and let's just go home and study by myself. But he didn't. So one student raised his hand and said, hey, professor, could you slow down a little bit because, I couldn't catch up, And he was like, look, if I have the time to finish writing with a chalk on the blackboard, you should have time with your ballpoint pen. Anyways, totally dismissing the request of the student. So that's a very important lesson for me throughout my learning years, that he wasn't giving me any drive to learn anything until my junior year when I took the class vibration. And in that class, the professor taught us the mathematics required to solve the vibration problem. And I was like, whoa, okay. So that's why you taught me this a couple years ago, because you want to solve that problem. Why didn't you tell me that? If you told me that we're learning this to solve that problem, I probably would have paid more attention to you when you taught me this. But you taught me in the subject as mathematics, so I'm learning mathematics because I am learning mathematics. My only drive at the time, I wouldn't say I have no drive. My only drive at the time is to get good grades. That's my only drive, because I have always been a good student. Just like you guys, you want to go to the best college, getting good grades should be your drive. But I don't want that to be the only drive in your study or in your course taking. You want to have a purpose, and I think if a student couldn't learn properly, it's 85% the professor's fault, because he didn't motivate you to learn properly. If you're learning the subject for the sake of learning the subject, then there's no drive, right? There's no drive. So number one, I want you to find the drive. If your teachers are not giving you the drive, you, as a youngster, as a fledgling youngster, should look for your own drive. Can you do that? Look for your drive. Give an example of the drive. In my junior year in college, we had this little project that we want to build a maze-solving robot. There's a contest. It's like a national contest with all the best students from the best colleges that they're entering that competition. Sort of like, a few decades ago, we had BattleBots? Heard about BattleBots, right? In this country. That was fun, right? That was fun. So if you're in a competition and you want to build the baddest, the meanest, the most powerful robot, you can menace your opponents. I mean, that's good drive. I mean, that's fun. So we had this goal. We want to build this little robot that would find its way from the outside skirt of the 16 by 16 grid to the center, which is the goal, as fast as we can. And you have 10 chances. So the logic is that you use the first chance to figure out the way, the shortest path, which is mathematically possible. And then use the rest of the 9 chances to go there as fast as you can, doing the shortest path. So in order to do that, and that's our drive. That is our drive. So in order to have this little robot that has a little brain, and that has the motors and wheels and brakes and everything has to work together, we had to look for information because none of that information was taught to us in the classroom. So we had to go to the bookstore, the actual bookstore, okay? Look for books, actual books. And then we don't have Wikipedia, we don't have nothing. So you go to bookstores, look in that section, electronics, mechatronics, so you look for how do you control a stepping motor, how do you control a DC motor, how do you put together a breadboard with microprocessor, how do you write
Vihan Shaw, come to counseling please. Vihan Shaw.
How do you write programs to drive this board? So that's our drive, and then we ended up spending many overnights in the laboratory for like 3 months in a row. And at the end of the day, we built it. We built a breadboard with electronics on it, with the most basic 6502 microprocessor. Not familiar with 6502? That's the microprocessor that drives Apple II computer. That was back in the day, 1980 something. That was the best we could get, right? So we used a very primitive microprocessor. We put together a very primitive circuit on the very primitive breadboard, and we put together some DC motors, heavy motors. We have 2 versions, and then we won the 2nd place of that competition. So that was good. That was good learning experience because we had to drive, so we had to go out there and find the knowledge we need, and the materials that we need in order to accomplish that goal. And everything we needed at the time wasn't taught in the classroom, because in the classroom it's just too theoretical. It is too, I would say hypothetical, but it's just like not very practical. That's where you get your good grades from. So anyways, that's drive number 1. I want to show you another drive that I had. That fast forward many years, about 3 years ago, my son, who was about your age, no, he was more than your age. He was already working for Airbnb in San Francisco. So one night he was coming home in the train. Unfortunately, when he was walking home in the dark alley, he was hit by a car. He was hit by a car and it broke his legs. Not just one leg, multiple bones. At the time, he was wearing black, all black, with a black umbrella, black backpack. Everything's black. And this car was making a U-turn. Obviously, in the rain, didn't see him. I don't blame this car because he was making a U-turn. He could not see this pedestrian walking on the street. He could not see anything, so he was hit. And he was rolled over by a wheel with one leg being pinched under one wheel. So that was pretty traumatic for me. I got a phone call, I rushed there, went to the hospital. After 3 months of rehab, then he was back on his feet. He was okay. But then I was thinking, what if he has some visibility? What if he has some visibility? And then probably he didn't have to go through this, because look, this time we got lucky because he was rolled over by a car in the right place. That's like, what if it's in his stomach? What if it's in his chest? Well, the outcome would be entirely different, you know? So I feel very lucky that I still have a son. So I was thinking, why don't we have a backpack that would just automatically light up when the kid is walking? It's too much to ask a child to turn on his backpack while walking. He's never gonna do that, right? So you wanna have a backpack that's battery powered, and the battery has enough power to be in the standby mode for a number of months, so not very frequent recharge is required. But whenever he's walking, this thing should light up. It's not that easy, isn't it? You need to learn the pattern of either walking or running before you can turn this up. And it shouldn't turn up when you're just handling this backpack, right? Just like you're opening the backpack and your books out and everything. So this pack should have a couple sensors. One is a light sensor. When it's really bright outside, there's just no need. So you have a photo sensor that will make sure that, I only look for the walking pattern when the light is low, right? And the second thing is that you would analyze the walking pattern or the vibration pattern to determine if this pattern fits the walking pattern. So here's a little Arduino circuitry that I just made myself, right? So in order to make this, again, I had to go to the internet, look it up, and found, there's something called Arduino, which is like a light years more advanced than the little 6502 I had. You know, everything is high level language, so easy to write, just easier than the basic. But then it comes to, it's more than writing the program, that you need some AI in it. You need to learn what is the proper walking pattern. Right? So I did some training of this circuit board, and here's how it works. I would simply connect my circuit board to my backpack because I've been shaking, so it'll, and then when I'm handling it, it doesn't turn on, right? It doesn't turn on, hopefully not. So when I'm just randomly handling with all kinds of vibration, you know, it hopefully doesn't turn on. But when I put it on my back and I start walking, let's see how it works. Voila. That's the AI in the simplest form, right? So you have some kind of a accelerometers, like 3 dimensions, and then you decide the kind of vibration you detected is walking or running, but nothing else. For example, you put this in the car is driving, it's moving, right? It should not turn on. Otherwise, it's kind of annoying, right? You don't want too many false positive. But some false positive, okay, but I don't want any false negative. So if it turns on unnecessarily, so be it, but I want it to absolutely turn on when you need it, right? So that's another drive. I built this in without thinking about money. Like, I'm gonna market this. I'm gonna go to Shark Tank to present to Mark Cuban so I can get whatever, right, from him for whatever percentage of my company. I wasn't thinking all that. I was thinking, what if this backpack can save one child? One. I don't need too many. Just give me one child. If I knew that false positive. If I knew my backpack can save one child from being hit by a car, and that's enough for me. That's my drive. So I want you to look for drives that you can see in your life. That's my drive. You find your own drive. There's plenty of examples in your everyday life. You can find a drive and you need to find a solution. And this solution may be important to you, but not important to anybody else. But it doesn't matter, right? It doesn't matter. If you want to learn something really, really good, you find your drive and then you learn something really, really good. Because by implementing a real life application, apparatus, device, that will force you to learn so much deeper than any classroom can offer you. So that's my drive. Another example, the maze solving, I think I'm pretty much done with the drive. So another point I want to bring out is that why I think machine learning, artificial intelligence, neural networks are good subjects for even high school students. Reason being is, if you want to build a space station, you need to learn a lot. You need to learn a lot. The background knowledge required to build a space station is really just too vast. And you guys have coursework, you guys have college application to worry about, you have extracurriculum, this and that. Amanda's got fencing. You know, people got stuff to do. You don't have the time. And you don't have the capacity until you have an IQ of 240. You know, like Terrence Tao, right? But most of us are not. So AI, in a nutshell, is a methodology. Neural networks, in a nutshell, is a methodology that doesn't have to support it by very, very profound and deep mathematics. You need some, but not a whole lot. Let me tell you what you need. You need a good understanding of linear algebra. Well, before that, you need a good understanding of algebra, right? And then you do linear algebra because you want to solve simultaneous equations. Heard about those? That's some knowledge, but not that hard. If you put your heart into it, you learn it. You will be pretty good at it in a couple days if you really put your heart into it. You want to learn linear algebra. And then what else do you have to learn? Some statistics, some probability. Oh, hey, these are the things that are covered by your coursework, right? You've heard about those things. Linear algebra, simultaneous equations, optimization, some calc. I'm gonna sidestep a little bit. I really like, because my son went to Homestead High School. When he was taking AP Physics, he was required to take Calc BC. That's AP Calc, right? I was really happy because there's no way you take Calc BC without taking AP Calc, AP Physics. AP Physics is the drive. You need Calc BC to be used to solve AP Physics problems. But if you only take AP Calc in a vacuum, then you don't have your drive. Why are we learning all this? You gotta know what you're solving for. Why you're learning calculus? Because you want to solve some real life physical problems. Unless you're in the pure mathematics, you get your satisfaction by solving this equation. Good for you. But for most of us, we have an engineering mind, we have a scientific mind. We want to know that this tool that we learn has applications that will help me to solve problems that matter to me. Right? So I don't know about you guys. Are you required to take AP Physics and AP Calc at the same time?
No.
So you can take them separately.
Yeah, most people.
I highly recommend taking them together because one is the drive, the other is the method, right? If you take AP Physics and you find, oh, how do I go about solving this? Oh, you need some calculus. Go back to calculus. Or you're taking calculus, you're like, what's the good use of this? I mean, why am I learning this? I mean, what is the point? You know, I just remembered my professor was teaching us Fourier transform. There are two domains. There's like frequency domain and there's a time domain. So the whole point of Fourier transform is to take a function and you apply Fourier transform against it to make it from a time domain to the frequency domain. And once you're there, you apply the inverse Fourier transform and to bring it back to time domain. I was like, cool. Why am I doing this? If you're gonna transfer it back, why do you transfer it there in the first place? You're going there and come back. It just don't go, right? So Fourier transform in a nutshell. is to figure out the frequency components of a random signal. I like to explain Fourier transform using a dish. Like if you eat bangchang chicken, it's really really delicious, and you know, this tastes so good. I wonder how you make it. So you apply Fourier transform to the bangchang chicken, and then Fourier transform tells you, oh, this guy, like, here are the components, here are the ingredients. You have a chicken thigh, right? You have 2 teaspoons of soy sauce. You have 1 teaspoon of chili sauce. You have sugar, how much? It tells you the ingredients, right? And then that makes it very easy to understand. Oh, so you have a random signal and you want to know the individual components of this signal. You subject that signal to Fourier transform, and then it will tell you the individual components of that signal. And then you can play around with those components. And then once you're done with playing around the components, altering the modifying, and then you can transfer it back. And you have another signal, which represents whatever you have messed with. That's really, really awesome. You know, like, if you heard about like voice changing microphone, like you speak to, like Amanda talks to a microphone, it comes up with my voice. That's totally possible because, you know, that's called digital signal processing, right? You apply some kind of a Fourier transform to her voice and you massage that with my characteristics, and then you play it back and forth, and you have me talking. So that's the drive. Okay, coming back to machine learning. I know you guys are in either in AI club or robotics club, and either of these clubs need some kind of AI, right? Just like the little robot that search for the optimum path. And then you need some mathematics background. The good news is that you don't need much. You really, really don't need much. What you need to be pretty good at artificial intelligence, what you need to be pretty good, not expert level, but for high school, to be pretty good at neural network, machine learning, you don't need much. You need basic understanding of calculus. Maybe not even Calc BC. You need maybe what's the other one? Calc AB? AB. Probably you need AB, right? This is the basic calc, right? So you need differentiation. You need to know the gradient concept, right? And then you need to know how to solve these equations. So you need to know linear algebra. So that's simultaneous equation. You're solving simultaneous. Linear algebra is all about solving simultaneous equations. In the world of numerical calculation, is all about solving simultaneous equations. Whatever you're solving, you're using finite element method, you do AI, you do machine learning. At the end of the day, you're solving simultaneous equations. But the only thing is when doing AI, because the matrix is so large, we can't solve it. And sometimes it's not even solvable. So we use another method, right? Have you heard about gradient descent? Yeah, right. So it's using tricks. But at the end of the day, you're trying to solve this matrix, and this matrix represents a series of simultaneous equations that you need to solve for. So it's really, really easy for high school students to pick up required background knowledge to be pretty good at AI. Therefore, I think that's a perfect subject for you guys to work on early on to get some exposure. This is not vaporware. This is for real, especially since a year ago, ChatGPT just came out of the blue, you know? Who would have thought generative AI could be this good? You don't have to write your homework anymore. It does most of the work for you. You know, a lot of times I don't have to write a lot of programs anymore. It writes perfect code, JavaScript, Python. You know, it just tell it what you want to do. It gives you pretty darn good code that runs and gives it may not be the optimum code, but it's a working code. So a lot of people are losing their jobs for this, and not to mention that the lawyers and radiologists and a lot of things the AI can do. So you guys, starting early, very good, very good. And it doesn't require a lot. It does not require you to take differential geometry, which I flunked. Well, proudly, because in Stanford, I was in the mechanical engineering department, but I had not a side job. I had my RA-ship sponsored by the robotics lab at Stanford. At the time, it's called robotics lab. The lab research topic was to find a path for a robot to go from point A to point B. Sounds easy, right? But what about there are obstacles? What about this point B is not even reachable? It's in an enclosure. Then this robot needs to be smart enough to open the door and come in. For people, human beings, that's second nature, right? But think like a robot. How do you figure out that you need to open this door in order to come in? So that was the research subject of that lab. And later on, that robotics lab became the AI lab today at Stanford. The professor at the time, the director of the lab, had moved on to another area. You would never believe. He moved into biology. How is that path planning? How does that have anything to do with biology? Oh, it's got everything to do with biology. Think about proteins. Proteins, they're like large, long chain molecules with all kinds of different shapes, right? And then in order to figure out the functionality of this protein, you not only have to know the composition of this protein, you need to know the 3D structure of this protein, what it looks like. And in order for this protein to be an enzyme, a whatever, or participate in other chemical reaction, you need to know if certain key elements could be latched onto whatever other molecule is trying to latch onto. So not only does the protein need to have this structure has to be accessible. For example, if you have this structure that will react with that molecule, but this structure is protected by another chain of molecules, then that structure, that other element couldn't get to it, right? So see where this pathfinding works? So the computer will figure out whether this path is even feasible. So this could be applied to a lot of new drug application, new drug discovery. Because in the world of pharmacology, I mean, you're looking for new drugs, and you have 22 million candidates, molecule-wise. And then if you were to do experiments, it's kind of taking time to go through all 22 million compounds in order to find out whether it works or not. But if you have a computer program that can apply this kind of path planning, maybe you will narrow it down to maybe 52. And then you can have your lab work on the 52 components, and then things are much easier. So that new area is new drug discovery, also called computational biology. Heard about that term, right? So anyway, so computer science has a very, very big impact on recent biology, because a lot of times the time-consuming components of the research can be replaced by high-speed computing, and that's going to change the way a lot of other disciplines move forward in the future, especially because the biology is something I know about. So that's why I brought this up. So just because you are learning a specific set of skills for this particular drive, for this particular subject or application at the time, that doesn't mean that your knowledge will not be applied to another entirely seemingly unrelated topic. Just like this robot to biology. Haven't thought about that, right? But that's the reality. So always keep an open mind to have a drive, to learn the basic skills, and once you're armed with the basic skills, you can look for other drives. And the more, it's like toolbox. You have so many tools in your toolbox, and then later down your life, then when you're facing with other problems, then you just have more things to work with. You just don't know which screwdriver you would need for that particular nuts or screw. So that's that. again, we live in an area that learning skills so much easier. I mean, you guys can learn from, I highly recommend Coursera. I highly recommend just take this Andrew Ng's course on neural networks. Octave is free, MATLAB is not. Just use Octave. Right? I don't know what you guys use. Python, you learn Python, you learn some Octave, then you can get started with easy classification problems. You can recognize letters. You can do simple things. That's really rewarding. But then again, that's other people's drive, you know. But I want you guys to think about your own drive. You're in a robotics lab. You're in robotics club. What do you want to make? Because only after you figure out what you want to make, then you can decide what you need to learn. Because a lot of things that you don't know what you need to learn. I learned this sentence very early in my life. It's called, you don't know what you don't know. There are two meanings. You don't know what you don't know. One is very mellow. It's like, oh, the things you don't know, you just don't know, right? You don't know what you don't know. Another is more obnoxious, that you don't even know what you don't know. That's kind of condescending, right? But either way, you really don't know what you don't know. You really don't know what you don't know. So have an open mind and build your toolbox. So you have more tools, and then life would be easier. Unless you're in an entire different path of your career that you're not, looking down the road, down the stretch, you're not doing any AI, material engineering, scientific, and then you become a poet. You might still need AI if you're a poet, right? It helps you, right? Anyways, you just can't escape. This is the trend. This is the future. I wanted to talk about some frameworks, but I don't think there's any need for that. You guys know more about TensorFlow, Microsoft Azure, and ML Studio. You heard about those? Simple tools. Those are tools. Doesn't matter. Whatever works. Whatever works. Because at the end of the day, just remember, that's just a bunch of libraries to help you maneuver matrices. Everything that's incorporated into any of these frameworks, just an easier or easiest way to maneuver matrices. It's all matrix operation. No more, no less. Very simple. Matrix operation. So get to know your matrices. They're very important, very important. Once you're in linear algebra, get good at matrices. Okay, don't be turned away. Don't be afraid of matrices. That's something you need to learn. Not that hard. Final thing I want to bring up is that when you're looking for your drive, look around your surroundings. Historically, a lot of scientific advancement came from nature, by observing what nature is doing. I'll give you a couple of examples. Many, many years ago, that was before the composite material was popular. Composite material, like carbon fiber, different layers with epoxy and all that. Before that, they found out that, beetles. Well, beetles are like flying around along the highway, and then when you drive along the highway, you see your windshield, a bunch of dead bugs, right? All kinds of bugs, especially moths and Notice that when your parents drive fast on the highway, the windshield and the front of the hood is kind of a dead bugs all over the place. Never a beetle. Beetles don't die. You can drive 75 miles an hour along the highway, a beetle hits your windshield, it doesn't die. Because beetles, they have shield. So the researchers were like, wow, what did beetle do? What's so special about this beetle? They experimented. They used a beetle and just hit it with 70 miles an hour, and the beetle survived. Awesome. All right, so the beetle, we got shell. So they pulled away the beetle's little shell, and they studied. It's composite material. Not only is composite material, the different layers and different fiber reinforcement are formed at the very specific angles. And only those angles work. Any other angle didn't work. So they mimic that structure. And that's the birth of modern composite materials. To learn from what the nature has done, millions of years of trial and error, and then humans come over and then say, hey, If you've done all the trial and error, you have debugged for millions of years, maybe we can just copy, and then it works, because that works, that works. Another example is that we have done some calculation on the pressure vessel. Suppose you have a cylinder, pressure vessel, and with caps, right? And then suppose you have P on the outside, and you have P0 on the inside. Suppose P is much larger than P0. How do you reinforce this cylinder? So after much elasticity, much profound mathematical calculation, we found out that you shall have 2 sets of reinforcement fibers at 75 degrees. And guess what? If you caught a shark, and you kind of study the shark, you find out the shark's got this 75-degree reinforcement already built in. You guys don't need to do any calculation, just copy the shark. Why does shark think that? Because sharks, they hunt in deep sea, and they come up to the more the shallow area, so they have to go through very large pressure variations. So when they go down to deep sea, a couple thousand feet, under the sea level, they build up the internal pressure. But when they surface, this pressure takes time to be relieved, right? So there is a huge pressure differential between the guts of the shark and the outside pressure. That's why the shark's body needs reinforcement. And that reinforcement coincides perfectly with our very, very profound mathematical elasticity calculation. It took us a long time to get to that 75 degrees, and the shark said, hey, I've known this thing for millions of years, and what are you guys doing? So anyways, learn from, and same with neural networks, right? Neural networks is that people are like, how do humans think? So they took apart your brain, and they did some study, and they found out, oh, there are neurons and this and that. Maybe we can just mimic that. So that's where they have different layers of neurons, of neural networks, different layer 1, layer 2, each layer doing different things. That's also mimicking what biology has been doing for millions of years. And you want to ask, why does that work? I don't know. I don't think anybody has. Well, I don't think anybody has stringent mathematical proof that today's state-of-the-art machine learning, why it works. So that's why at the beginning I said it's a methodology. It's a method that people developed that works. And then if you have enough intelligence, you put enough time, you can further perfect this technology. You can perfect this methodology, so it will work better. But there's another branch of study, which probably will be outside the scope of this talk, that people are really good at mathematics. They're probably trying to figure out why that works. But that's not our problem, because that's not my drive. That's probably his drive. For people, they will get maximum satisfaction by figuring out something that don't bother us, right? But it bothers him. That's fine, So anyways, so AI does not need very, very deep understanding of the underlying mathematics, because there's none. There's no stringent proof to prove that the current AI machine learning neural networks methodology works. Why it works, I don't think anybody has a stringent proof for that, but it simply works. And then that fits the high school student genre. That it's perfect for you guys to pick it up. It's useful. It's not that hard, and it's satisfying. So the only thing left is for you guys to find a topic, to find your drive, to find your backpack. That's my drive. To find your backpack. What's your backpack? Look around your environment. Look at your household. There's gotta be problems to be solved. and a lot of problems can be solved by AI. And a lot of problems that we didn't even know was possible to be solved by AI has been solved by AI, just like Napoleon, right? So, anyways, I think my time is up. That's all I'd like to cover. You want to take a little break, and then we can.
Hi guys, let's have
Done? System.